Section 3.8 is on differentials and marginal analysis. So what is a differential? Well, let's read the definition right here. It says definition of differentials. Let y equal f of x represent a differentiable function. The differential of x, denoted dx, that's what we've been using, dx the entire time, is any non-zero number. The differential for y is dy. So when we've been writing y prime, that's the same thing as dy. That is the differential. Okay, but what I want you to notice here is the definition of a differential is dy equals f prime of x dx. So what I'm going to do is, rather than reading the rest of this, I encourage you to read this. I'm going to show you a visual representation of what are we actually doing. So what we've been looking at the entire semester is what is the slope of a tangent line, which is the same thing as what is the derivative at any given point. So if you have a given point x right here, and you find the derivative and you plug in x, that's going to give you your slope. So what's the idea? Why do we care about the slope of a line? And the idea is we can use the slope of the line, the derivative, to estimate the next value. So for instance, let's say you're a company and you've sold 1,000 things. What's going to happen when you sell the next 100 things, or the next 10 things, or the next 1,000 things? What's going to happen in the future? And the idea is we can use derivatives to estimate what's going to happen in the future. A derivative is just an estimation. So what's the idea? We're going to have an x value that we pick. So if I sold 1,000 units and I want to know what happens in the next units, my dx in that case that I'm talking about would be 10. My dx, which is my estimated change in x, is the same as my actual change in x. So dx is the exact same thing as delta x, delta representing the actual change. Okay? So what happens is if I find that derivative, at that point x, I found the slope of the line, and if I multiply that times x, what that's giving me is dy. dy is the estimated change in y for the given change in x. So dy is the estimated using the derivative. And again, we find dy by taking the derivative at that point times the change, or the estimated change in x. Okay? So that green one, the dy, is the estimation that we get for the future using derivatives. However, there's the actual change in y, what actually happened, which I just colored in black. That's called delta y. To find delta y, it's pretty simple. All you're going to do is f of x2 minus f of x1. You just do the actual change in the y values of the function. So delta y is the actual change in y. dy is our estimated change in y by evaluating the derivative at the given x value and multiplying it times the change in x. So those are the two things that we're going to be calculating and comparing. How accurate is the estimated change, dy, to the actual change, delta y? How accurate are those two things? And what we find out when you do more and more examples is the smaller that you do the change in x, the more accurate the estimated change in y is. So we don't want dx to be large values like 1,000, 100, or 10. Usually we're going to have dx be very small values like 1 or 0.1 or 0.01. And the smaller the change in x is, the more accurate the change in y is, the estimated change in y. And that's what it says right here. It says, so dy is the estimated change and delta y is the actual change. If dx equals delta x, if the change in x is small enough, then dy is a good approximation. The estimated change in y is a good approximation of the actual change in y. So we have two things that we need to find. The first thing we need to find is dy. How do you find dy? Find the derivative, plug in the x value, and then multiply that times the change in x. So find the derivative, plug in the x value, take that value, whatever you just got, and multiply it times the change in x. Continue on to see what we do for the actual change in y.